Let's do one more here. The last one from this particular note. Okay, we're used to this shape. We know this shape, but we now have a top on it and a couple other things here. Okay, so a closed box with a square base is to contain 252 cubic centimeters of interior space. The material at the bottom costs 5 cents per square centimeter. For the sides, it costs 3 cents per square centimeter, and for the top, it costs 0.2 or 2 cents per square centimeter. We need to find the dimension that will minimize the cost. Okay, so it's a typical minimal cost, right? If it was a shape that we were building to contain something, we'd want to, and we had to build quite a few quantities, we'd want to make sure that the cost was minimized. And we have a certain amount of material based on different prices. The different prices represent maybe bottom might be a different material, the sides might be a different material, and the top might be a different, maybe cheaper material. And the interior box has to be the constraint here of 252. The sizes always have to be 252. Might be a liquid or a fluid product that was in there. It might just be an object that's contained in the box. Either way, that's kind of what we're doing here. Okay, so here's our constraint equation. Let's develop the constraint equation first. Okay, we've got 252, and that's a volume, right? And we want to minimize the cost. So the volume is under the constraint here, and the volume, okay, is x squared times h, right? That's the base. X squared is the base, so length times width times height, and that's 252, right? So it's x squared times h is 252, and I'm going to solve for h here. Okay, and that's 252 x squared, or we know that to be. Okay, good. Now, I'm going to talk about, we didn't do this in the last question, but I'm going to talk a little bit about the domain restriction on x, on our variable. Our function is going to be a cost in terms of x, but I want to talk about the interval restriction. So what are the possible values of x? Okay, now this doesn't take too hard to come up with the lower boundary, and I'm going to write it up here. Okay, so clearly, okay, x has got to be greater than 0. If x was 0, we wouldn't have a shape, and if it was slightly just bigger than 0, we'd have a really, really tall, narrow, like a small base, and a very, very tall height. So we'd have a box like this. Okay. Okay. And it can go up to, well, we have volume, we have volume to work with, and the height would be the way to do this, to come up with the higher boundary, is to think about, okay, the height would be, in this case, all of the 252 square centimeters would be used for the base, and the height would be 0. Okay, so it would be a really, really small height, okay, but okay, a really, really large base, okay, stretched out. And since I have 252 square, since I have 252 cubic centimeters to work with, my height I'm going to neglect, in a sense, just have a really, really small value of my height. My entire base, the x squared component, would be and could be used to get that 252. So the upper boundary is the square root, because the base is x squared, right? The square root of all of the remaining amount, so that's 252. So the square root of 252, whatever that would be, I think I have that down to about approximately 15.87. So in some ways, we're looking for an answer that lies between 0, okay, and just under 16 centimeters. Now, our optimal equation, okay, is going to be our cost, okay, our cost function. So that's the one I want to minimize. Now, our cost is a little different, okay? Our cost, okay, I'm going to write it in terms of cost function first, okay? And let's do the base. Okay, the base costs 0.05 cents per square centimeter, and the base is made up of x squared. The top I'm going to do next. The top is also an x squared, okay, but it's 0.02 cents, okay, or dollars. I'm going to write it in terms of dollars. And then the sides are 3 cents a side, okay, so $0.03. And I have 4 sides, and the dimension of each side is xh. Okay, so can I turn around and write that as a function of cost in terms of x? Well, I sure can. I don't have to change this one. On my next line, I'm going to add these two together. They're common terms, so I'll do that in a sec. And I want to just substitute here for h, and we found that to be 252 x to the negative 2. Okay, let's do some simplifying. 0.07 x squared. Okay, that's 0.05 plus 0.02, and then the product of 0.03 times 4 times 252. I have in my notes 30.24, and my variable is x to the negative 1. And that's my cost function. Okay. Now I think we probably know what to do next if you're doing some of these homework questions. Okay. At this stage, we take the derivative. Okay, and we have 0.14x negative 30.24 x to the negative 2. And I want to solve this to find the minimum cost, right? Minimum cost. So I solve this, set it equal to 0 and solve. So I've got my negative term is the negative 30.24. So that's the one I'm going to bring over. And while I bring it over, I'm going to also isolate my x to the power negative 2 down to the denominator. That way I'm dealing with positive exponents. Now I can cross multiply. Now I can solve for x. I think I've got 30.24 divided by I don't have a calculator with me. I have to bring it down the next time here. I think the division of that is 216, and that works out to be a nice, that's centimeters. Okay. So the base x has to be 6. That has to be a 6 by 6 box, and that falls in my domain interval for sure. Okay, absolutely good. H would be, I've got H, I don't think I calculated H. What would H be? 252 divided by 36, whatever that is, 252 divided by 36. Gonna have to wait for that one. 252 divided by 36. 7, the height is 7. Okay, so my dimensions are 6 by 7. That's usually the common notation for that. So length, or length times width times height. Okay, I left some space over here. I want to just do one little thing, and that's to find the calculations of the cost here. So we should, back in section 3.2, we did endpoints as well. So that verifies a lot of this stuff. And I'm going to put the cost into my cost function right here. So I want to find the endpoints. I want to find the cost at about $0, just really close to 0. Okay. So what is the cost at 0? What is the cost at 6? That should be my minimum cost. And the cost, the last one, the other endpoint, is the cost at, what did we say, about 15 point, I think it was 87. That was the square root of 252. Okay, now I don't exactly have these values, but what I'm going to do is just take a second and put them into Desmos. So I'm going to minimize this for a second, and I'm going to call up Desmos. Okay. I should have had this open, sorry, my apologies. Now I'm going to put in my cost function. Okay, and see if we can see this. My cost function, I've got 0.07x squared plus 30.24x to the -2. And my interval of restriction is over here. Okay, so between, it's going to, oh, it's not -2, it's -1. Okay, that's a little bit better. Okay, so that's my minimum point at 6. That's verified on the graph. That's good to see that right there. That's pretty neat. Okay, so I can use my calculator. Oh, undefined. Whoa, okay, that must be an asymptote at undefined. But remember, it wasn't exactly 0, right? Okay, my cost function is a little bit above 0. Okay, that's how I have to write that. It's not exactly the cost, but it's a little bit above 0. So I'm going to put that plus sign, actually. I'll write it like this. Just a little bit on the right side of 0. So let's go back to Desmos, okay, and get my values here. Okay. So what would these values be? Okay. So I can't use 0, but I could certainly use, okay, that looks like it's approximately, okay, $302,400. The next cost is the cost at 6, $7.56. Okay, and the next cost, and I'm going to be a little bit more accurate. I know I rounded it to 50.87, but it's actually, okay, the square root, okay, of 252, okay, and that's 19.549. So I'm just going to write these down. Around that to 19.55 cents. Okay, so back to my, okay, like showing almost done here. Okay, so we got, what did I say here, 302,400. Okay, now that's a high one. That makes some sense though. Okay, that at that 0, okay, that's when, okay, we've got okay, the large, very large. It's an asymptote, so it's a sort of an infinite value. $7.50 here, 19.5. Okay, so Desmos will show you that minimum. Okay, and it's verified by checking the derivative point, the extreme point, plus the 2 endpoints. Okay, that's it for that one. That's going to be the only recorded part of this.